What happened? Whoa, wait a minute. Parts aren't burned and others aren't even cooked? That turntable sure wasn't rotating, which means the standing waves weren't equally distributed. Haven't got any cooking clue what I just said? No worries. Would you give me 3 minutes to explain it all in plain English? Deal? Let's get started then. Microwave ovens generate an electromagnetic traveling wave of certain frequencies. When a wave reaches the other side of the oven, it inversely reflects to interfere with itself, creating a special wave that just vibrates up and down while standing in its position. Hence the name, standing wave. You can easily notice that the disturbance of the wave at these points is zero. These regions are called nodes, which have no energy at all, so they don't cook our food whatsoever. You can also notice that the disturbance is greatest at these points. Well, these are called antinodes, and these have the most energy. It is at these regions where our food gets cooked the most. Turntables therefore rotate the food in the oven, ensuring a uniform access to the antinodes. Otherwise, you will get what happened to your sandwich. Very interesting, right? Wait, I haven't started yet. As we saw, two waves interfere to form a standing wave. This interference is explained by superposition, which is nothing but addition really. Let's apply superposition now. At these points, assuming for simplicity the amplitude is 1 meter, we get 1 plus minus 1 equaling 0, and at these points 0 plus 0 equals 0. Since both waves added up to form something smaller, this is called destructive interference. The result at that instant is therefore a perfect straight line. After half a period, at these points we get 1 plus 1 equaling 2 meters. Since both waves added up to get a bigger wave, we call this constructive interference. And these points form the antinodes. At these points, however, we get 0 plus 0 equaling 0, which are points on the line, forming the nodes. The resultant wave at that instant is therefore a wave with twice the amplitude. At the end, we get a wave which alternates between a harmonic wave and a straight line, aka a standing wave. We said earlier that both waves must have specific frequencies. Otherwise, they will generate a mess of reflected waves that won't form any pattern. But what are these specific frequencies? Well, that's easy. Since the wave can't move at fixed ends, the smallest frequency is half a wave, with 2 nodes at the sides and 1 antinode. If we apply few simple equations, we will get this equation. This frequency is called the fundamental frequency, or the first harmonic. And here is where all the magic begins. Keep this formula in mind. The second harmonic is a whole wave, aka the first overtone. Then the third harmonic, the second overtone, and so on. Thus, we deduce that all the other harmonics are simply multiples of the fundamental frequency. Standing waves phenomenon exists not just in electromagnetic fields and microwaves, it also exists in many other fields. It also not just occurs in closed stationary mediums like a microwave. For example, it can also happen when a traveling wave moves opposite to its moving medium. It can also occur in many other scenarios, each with different magical formulas. Not to mention that standing waves are applied in numerous amounts of applications, ranging from every person's daily life to the most advanced scientific applications. I'm done. Quick, you must catch your bus. Oh, and remember to read more about standing waves and share your knowledge with your friends.